exist an invertible matrix P such that P inverse AP is a diagonal matrix. If A and B are similar matrices of n by n dimension, then they have the same eigenvalues. So, we are also given the condition to make it diagonalizable. I have the result after multiplying the inverse matrix P by the matrix A and the matrix P, it should give us a diagonal matrix. Matrix A given the elements 1, 3, 0, 3, 1, 0, and for the third row, 0, 0, negative 2. Next, we have matrix P given as 1, 1, 0, 1, negative 1, 0, and 0, 0, 1 for the last row. Okay, now we have to check if they would be similar matrices. The result of their eigenvalues should be the same, basing it from our theorem. Okay, and then later on we would check. So the result of P inverse AP should be a diagonal matrix. By cofactor method, so we have this, and then it's minor now, determinant of our minor. Okay, so determinant, product minus product. Let us simplify. So binomial square, and then we have minus 9. Simplify further, we would get lambda square minus 2, lambda minus 8, and then the other factor. So we would factor this out. I have lambda plus 2, lambda plus 2, and lambda minus 4. Let us now solve for our eigenvalues, or the lambdas. We have it as negative 2, and 4. So your eigenvalues are negative 2, which has a multiplicity of 2, and 4. Get the inverse matrix of P and multiply it by AP to get our diagonal matrix, which would correspond to the eigenvalues of our matrix A. We have solved for the eigenvalues of A to be negative 2, negative 2, and 4. So now, we are given matrix P as 1, 1, 0, 1, negative 1, 0, and 0, 0, 1 for the row entries. So, our first step is to calculate its inverse matrix. So, by matrix inversion, I have matrix P on the left side and your identity matrix, which would have a dimension of 3 on the right side. So applying your raw operation, I would need to have negative R1 plus R2 to get my new R2 to eliminate, to make this as 0. So I have the second row now would have the entries 0, negative 2, 0, negative 1, 1, 0. And then retain the third row since we have our 0 element already. Next, let us refer to this operation now. I have negative 2 for the second row element, so I need to make it into an identity or a leading element. So I have to divide the second row by negative 2. So dividing negative 2 for the second row, I would have my new second row as what? 1, 0, 1 half, negative 1 half, 0. Okay. I have my leading element now for the second row. Next step is to make this element as 0. So, operation, we have negative R2 plus R1 to get my new R1. Okay. So, applying, this would now be what? First row is 1, 0, 0, 1 half, 1 half, 0. Retain the second row in the third rows. Okay. So, this is an identity matrix already. Therefore, this would correspond to your inverse matrix P. So, I have inverse matrix P. Next step is to have the product of your matrix A and matrix P. So, I have product, row by column entries. So I have 1 by 1 plus 3 by 1 plus 0 by 0. Next, first row, second column, I have 1 by 1, 3 by negative 1, and 0 by 0. Next, first row, third column, so I have 0, 0, 0. And then, for the second row elements, so I have row by column still. So, second row, first column, so 3, 1, and then 1, negative 1, 1, and then 0. Next, for the second column, 3, 1, 1, negative 1, and 0. Next, second row, third column, so I have 0, 0, and 0. Next, for the third row, okay, multiply again by the column matrix. Okay, so I have 0 by 1, 0, 0, negative 2, and 0, which still be 0. Next, third row, second column, so all 0 still. And then for the third row, third column, I will get negative 2. Okay, simplify. I have 4, negative 2, 0, 4, 2, and 0. Third row, negative 2. Okay, so this is now your AP matrix. So from our definition given here, the diagonal matrix would be obtained from getting the product of inverse matrix P times AP. So now, okay, multiply the following. So we have solved for AP already to be 4, negative 2, 0, 4, 2, 0, 0, negative 2. Okay, so here. And then we have inverse matrix P from our solution earlier. Substitution. Okay, now have your product of matrices. So yeah, first row by first column, first row by second column, first row by third column. Next, second row entries by the first column, second row by the second column, second row, third column. And then for our last row, first column, last row, second column, last row, last column. Simplify, you would get 2 and 2 plus 0 would give us 4. This would just be 0, 0. Next, I have 2 minus 2 would just give us 0. Next, I have negative 1, and then negative 1 would give me negative 2, 0 still, 0, 0, this would be negative 2. So, we have our diagonal matrix, which would correspond to our eigenvalues as 4, negative 2, negative 2. As given in the eigenvalues of A, which we have solved to be 4, negative 2, negative 2. So it's the same. So from the given theorem, matrices A and B are similar if they have the same eigenvalues. So we have proved that matrix A and matrix P are really similar matrices because we have the same eigenvalues for matrix A and matrix P. Questions?